Right, so over to you, Mark.
Yeah, I know we have to finish on time because I know that we mustn't annoy the physicists. So, and I'm going to lower the tone anyway by talking about, well, I was going to apologize because I'm really a semi-group theorist. But the Daily Mail headline I got from Andy's talk is basically everything you're doing is a footnote to semi-group theory. That's what I got out of your talk, Andy. What I'm going to talk about is actually related to what Samson was talking about, but I should perhaps first of all explain why or how Phil and I got talking about something so apparently far removed from what you guys are generally interested in. It is connected with Phil's book with Jim Lambeck. What happened was, and also Girard is also going to come into this story. So a lot of names have been banded around. So I had no clue who Girard was. And Peter Hines came into my office one day and he asked me if I would be his PhD supervisor. This was a long time ago when I was in Mordor. And I thought I would be very clever. My answer to him was, I tell you what, if what you're reading has inverse semigroups in it, then I will be your PhD supervisor, thinking, of course, that there was no way. And he was reading Geometry of Interaction 3 by Girard. So I thought I was on pretty safe ground. So you can imagine my horror. Well, I think it was page 9 of the preprint. There, as clear as day, was an inverse semigroup. I was very honest with Peter. I said, yep, this has inverse semigroup. So he became my PhD student. And he got interested in linear logic. And through that, he talked to Phil Scott because there were some connections with the book by Lambeck and Scott and linear logic. But like Samson, I went off and I sort of didn't understand what Girard was on about. So I just did some semigroup theory and stuff like that involving partial injections, which is what this talk is going to be partly about. And subsequently, I mean, I was at that time a long way from Edinburgh, and then I moved to Edinburgh. And it was then that I really got to know Phil Scott because, as you've just heard, he liked Edinburgh a lot. And he got in touch with me, I think this was a few years ago, and he introduced me. I used to go and talk to him at the School of Informatics, which I'd never been in because it had lots of frightening computer scientists, and I didn't think it was for me, but I went there anyway. And so we got talking. And what I liked about Phil was that he liked to talk. So, we would joke and, you've heard the stories about Phil. And then gradually we sort of honed in on what we were both interested in. And this is what I'm going to talk about today. And it's a long way removed on the surface from what everyone else has been saying. But there is a connection with Girard's work in that operator algebras lurk, and I think that's the correct word for operator algebras, they lurk in the background to what I'm going to talk about. So we did manage to write a paper. Am I pushing the right button? Ask you because there we go. How did you do that?
I pressed this button here.
Oh, you pressed that button. Okay, I will try not to press the button that Robin pressed. So, which I have no idea what that is, and neither do you. So we managed to write a joint paper together, and we've also got one submitted. Phil was extremely meticulous, so we write something, and then he would go through it with a fine-tooth comb. So I'm definitely going to miss that. So any misprints or typos are entirely my fault from now on. So what I'm going to do is, it's a purely mathematical question. So, and there is a connection with logic, but it's kind of hidden. So back in the, I guess it's 1920s, 1930s, Łukaszewicz introduced Aleph naught valued propositional logic, and then it went into abeyance. And then Chang introduced MV-algebras in the 1950s. That's C.C. Chang of Chang and Keisler fame. And I'm going to tell you what all these things are, so don't worry if you don't know what they are, because I didn't either. So MV-algebras are to Aleph naught valued logic as Boolean algebras are to two-valued logic. So there's some kind of generalization of Boolean algebras. But I also, had a generalization of Boolean algebras, namely Boolean inverse monoids. And this is where the connection with operator algebras comes in, because you can generalize classical stone duality. Exactly the same proofs basically work. So you go, instead of Boolean algebras and topological spaces, you have Boolean inverse monoids and certain kinds of A-tail groupoids. And this is sort of behind a lot of what C-star algebras are actually interested in. The C-star algebras that they construct are often constructed from topological groupoids, particularly A-tail topological groupoids. So there are two possible generalizations of Boolean algebras, and the question is, how are they related? So it's a typical mathematical question. And neither is a subset of the other. Okay, so the relationship is not an obvious one to begin with. And this is what we sort of became interested in. And there are other things connected with this, which I will come to a bit later when I come to the end of the talk, which Phil got particularly interested in. So the aim of this talk is really to show you how these two purported generalizations of Boolean algebras are related to each other. Okay? So I'm going to tell you what each of these things is, and then I'll tell you the theorem, and then I'll finish up by just having some examples and also further work. Now, MV-algebra. When I first saw this, particularly the last axiom, I refused the fence, as the horses do at Royal Ascot, because I just thought, I have no idea what that means. I'm going to show you what that means in a minute, because you all kind of know what it means. And I'll show you that in a second. The first bits I was quite happy with, it's a certain kind of monoid. We've heard a lot about monoids. So it's a certain kind of monoid. It's a certain kind of commutative monoid. So that's an MV-algebra. In fact, in Chang's original paper in the 50s, you won't see specifically those axioms. You see something much more complicated. This is the boiled down version. So that's an MV-algebra. M stands for multiple value, by the way. So, and that's the connection with the logic. So you need some examples of this thing, okay? And of course, every Boolean algebra is an example. And in fact, the last axiom is simply that thing involving implications, which you all know about. So it's kind of amazing. So if you have a structure, a set, and you have something like a join, something like complementation and a zero, and this axiom holds, and the ones for an MV-algebra, and everything is idempotent, you have a Boolean algebra. So Boolean algebras, as you would expect, are examples of MV-algebras. In fact, the Boolean algebras are precisely the MV-algebras in which everything is an idempotent. So it's not commutativity that fails, it's idempotence that fails. A nice simple example to show you that these things are not vacuous, so they really are examples of MV-algebras. If you take the unit interval and you do addition until you reach 1, and then you just loop at 1. That's the join operation. That's the plus. And then the negation is simply what you expect. It just flips everything. And then the finite ones, or some examples of finite MV, these are, of course, this is an infinite, but an example of a finite one, number 3, you can see that you just take fractions, all the fractions from 0 up to 1. And when you take n equals 1, you get the 2-element Boolean algebra. So even finite MV algebras don't have to be Boolean algebras, okay? So, and there are various results about MV algebras. So as I said, if everything's idempotent, you have a Boolean algebra. The last one is particularly interesting. I'm going to give you a concrete example of this a bit later on. The finite MV algebras are isomorphic to finite direct products of the MV algebras of that form, L over n, L sub n. Now you know that the finite Boolean algebras are isomorphic to direct products of the 2-element Boolean algebra. So this is a direct generalization of that theorem. I'm going to show you how there's a connection between that last class of examples and what I'm going to call Boolean inverse monoids. Okay, so that's the MV-algebra background. They generalize Boolean algebras. Now, for inverse semigroups, Boolean inverse semigroups, the only thing you have to remember, because I'm going to introduce an abstract definition in a second, but the only thing you have to remember is that the abstract forms of this concrete example, which I'm going to go through. Okay, so if you just remember that, you'll be fine. So imagine a set, let's say it's non-empty, and you look at all the partial bijections of that set. So what I mean by partial bijection, I mean a bijection between two subsets of that set. And that's a monoid under composition of partial functions. And you're allowed to have a zero because that's, that causes all kinds of controversy amongst some people, but the zero is just the identity function on the empty set. Okay, and we've got a 1 in there as well, so it's actually a monoid. Now, it satisfies these equations. So if I pick any element f, any partial bijection, I look at the equations f equals fgf and g equals gfg. So g is some unknown. It not only has a solution, it has a unique solution. And it's obvious what it is. If you have a partial bijection, f, it's just a partial bijection that goes the other way, f minus 1, okay? But it's unique with those properties. The only idempotents, remember the things e, so e squared equals e, the only idempotents are the identity functions on the subsets. And this immediately tells you, because if you multiply two identity functions on subsets together, you get the identity function on the intersection of the two sets. So it immediately tells you that the idempotents commute. That's a very important fact. If I take two, there's an ordering. One partial function is less than another, but that can be described purely algebraically. So f is less than g means that g restricted to the domain of f is equal to f, but the domain can be replaced by the identity function on the domain of definition of that partial function. So you have a purely algebraic definition of the restriction relation on partial bijections. That's also important. It's not imposed from outside. It comes from the algebraic structure. If you take two partial bijections and you just glue them together, the result will generally be a binary relation. It won't be a partial bijection. So you have to have some conditions that are satisfied. And of course, there are two conditions, one on the domain and one on the images. And the conditions become purely algebraic. So if I give you two partial bijections, f and g, then their union is a partial bijection precisely when fg minus 1 and f minus 1g are idempotents. Okay, so that's the abstract form, and everything can be converted into the algebra of that particular monoid of partial bijections. And now I'm going to give you the abstract definition of an inverse semigroup, and then I'm going to tell you what a Boolean inverse semigroup is. So the abstract definition is, so we take as our starting point the fact that every partial bijection, there is a unique partial bijection that undoes the effect. So we then convert that into pure algebra. So we're going to say that a semigroup is inverse if for the equations x, so x is your known here, so x equals x, y, x, and y equals y, x, y have a unique solution for y. And we'll call that x to the minus 1. Okay? So that, and if you check, you can see that the concrete examples I've given are inverse monoids in this sense. As I say, the best thing to do is to think of the elements of an abstract inverse semigroup as being abstract partial bijections. All the things that you expect work. In particular, the idempotents commute. It's not obvious. It's one of those things that we say is elementary but non-trivial. Okay, so this was discovered way back in the 50s. Roger Penrose, for example, was one of the people who first wrote a paper on this stuff, believe it or not, when he was interested in generalized inverses. Now, if you think about the set of all partial bijections on a set, It has a lot of extra structure. And this is what's going to be the basis of my definition of a Boolean inverse monoid. So first of all, we have the ordering that we can define in exactly the same way as we did for partial bijections. So we've got potentially meets and joins, but you have to be very careful with joins. So it is not true in general, unlike in lattice theory, that if you pick a pair of elements, they can have a join. There's a prerequisite that must be satisfied, just as you had with the case of partial bijections. So if xy minus 1 and x minus 1 y are both idempotents, then we're going to require that their join exists. That's a prerequisite. That's the minimum prerequisite, and we're going to require that the join exists. We're going to require that multiplication distributes over joins from the left to right. And we're going to require that the idempotents form a Boolean algebra under the induced ordering. Okay, now there is a connection already, and this is what guided us in our work with operator algebras. Because if you take so IN1, that's the set of partial bijections on a finite set with N1 elements. It looks a little bit like the set of N1 times M1 matrices over the complex numbers with lots of complex stuff thrown out. If you just have the zeros and ones, and you make sure that no column has any repeats and no rows has any repeats of non-zero entries, so you can have at most 1, 1 in each row and each column, then you've just got a copy of IM1. So somehow there is a connection with finite dimensional C-star algebras. If you take a direct product of matrix algebras, you get a finite dimensional C-star algebra. And this is what guided us. So we were looking at what had been done for C-star algebras, but we were thinking about partial bijections. Okay, so this is quite an important result. So now, I give you a so what is the connection between Boolean algebras and Boolean inverse monoids? And it's not direct, it's a coordinatization theory in a very similar way to the Murray von Neumann coordinatization theory. It's a very similar in feel. Now, first of all, I'm just taking an arbitrary Boolean inverse model. We're going to have to specialize in a moment. So you take, for each idempotent, you take all the idempotents that are connected to it, meaning that there is an element which has that idempotent as a domain and then the other idempotent as a range. So you get an equivalence relation on the idempotents. And we would like to define an everywhere defined operation, but this is going to be a partial operation for the time being. So I take two equivalence classes, one containing E and one containing F, and I define their sum only when I can find something E prime and F prime, which are orthogonal to each other, but are connected to the idempotents E and F. So I get a partially defined operation. I can take their join, and then I take the equivalence class containing their join. So the problem is there isn't enough room. So imagine that you're looking at partial bijections on a finite set. You can sort of add things as long as the two things are not too close together, and then you get stuck. You get a partially defined operation.
Is this functorial and does it give an adjunct?
Yeah, it will be functorial, yeah.
Does it give an adjunct between effect algebras?
I have no idea. No, I'm going to come back to that in a second about effect algebras. I'll come back to that in a moment. That's an open question. Now, the problem is we'd like to complete this to an everywhere defined operation. So we have to impose some extra structure. So we've got our Boolean inverse monoid, and the first thing is we're going to require that every element is beneath a unit. Now, don't get carried away and think I can just replace everything with a group, because of course a given element may be beneath lots of elements which are invertible. I just need that one exists. That's the first property. And the second property is the principal ideals should form a lattice. Okay, now, so I'm going to say that a Boolean inverse monoid with these two properties is a Foulis monoid. Okay, so it has these two properties. Now, why these two properties? Now I'm going to show you why these two properties. So this is where the MV-algebras come back again. Because of the first property, I can define a negation operation. Now, the E bar simply means the complementation in this Boolean algebra. Okay, that's all that means. And I can extend the partially defined operation, which is defined using only orthogonal idempotents, to an everywhere defined operation using the fact that my principal ideals form a lattice. So the intersection of any two principal ideals is a principal ideal. So in this way, with every foolish monoid, if I define the structure LS, which is this collection of equivalence classes of idempotents, remember the idempotents form a Boolean algebra, what I actually get is an MV algebra. So the question is does every MV algebra rise in this way? I mean, it could go either way. Now, what we did, we looked at some work by Daniele Modici, who is probably the best known for working on MV algebras. And he obtained an answer using AF C star algebras. And that seemed to us not wrong, because of course the theorem was correct, but it felt wrong. After all, a Boolean algebra shouldn't be described in terms of an operator algebra. It should be described in terms of something algebraic. So, oh, that could be a hint. Get a move on. Yeah, I have no idea. Well, you can see anyway. But I think at some point we're going to get thrown out. So let me give you the punchline. So we proved that darkness is descending, literally. By the way, I took great exception to your comment about Edinburgh being in the dark. Sometimes the sun emerges. So every countable MV algebra can be coordinatized in this way. And in fact, if you take the finite symmetric inverse monoids, in other words, you take a finite set, you take all the partial bijections of that set, that's an example of a Foulis monoid, and every finite MV algebra arises from a direct product of these things. So the finite symmetric inverse monoids, so these finite Boolean algebras, which have certain properties, give rise to all of the MV algebras. Now, we had countable. Now, apparently there are coordinators beyond countable. I'm not entirely certain I believe in them, but apparently there are. And luckily, somebody else was able to kind of finish off the theorem that we'd started. So Phil and I proved this result. And we were looking at papers on operator algebras and AF, which means approximately finite. And we decided that you didn't need any of this operator algebra stuff. It was, in Sampson's word, a red herring, and you didn't need it. So what actually was proved by Fred Véron after we proved our theorem was that every MV algebra can be coordinatized in this way. Every single one, which is a remarkable result. He proved it using completely different methods. Now, you might wonder where the Boolean algebras come from. Now, the Boolean algebras are coordinatized by the Boolean inverse monoids that have central idempotents. And those are pre-sheaves of groups over Boolean algebras having certain properties. Yeah. It's not obvious, but that's what they are. That's a theorem of semigroup theory. We occasionally prove theorems. Now, the question that I was asked was really about effect algebras. And the answer is, this was something that Phil got very interested in. Having done that, we proved that theorem. What about effect algebras? And the answer is, we don't know. So the question is, so we know that some effect algebras can be coordinatized in this way. I would be very surprised if every effect algebra can be coordinatized in this way, but it is an open question, which effect algebras. It doesn't matter if you don't know what effect algebra is, it's a generalization of an MV algebra. These are interesting to other people. There's a sort of.
Just know they've got nothing to do with algebraic effects.
Yeah, they've got nothing to do with algebraic effects. There's topos theory, which, as we know, is really applied monoid theory, and then there is a vectors theory, which we would like to prove is really monoid theory as well, but we don't know.
Now I find out there are things called foolish monoids.
Yeah, foolish monoids, yeah. And polished spaces. And so I have to thank Phil, my collaborator, without whom this would not have been possible. I greatly enjoyed working with him. We had Skype meetings every couple of weeks. And as people have mentioned, we would sort of joke and lark around. And then eventually we would sort of glide into talking about maths and find the things that interested us. And that was a great way of working. You know, rather than somebody coming with an agenda, we found the things that we were both interested in. So a lot of what we did has appeared, but not everything. So we did do some work about Bradley diagrams and Boolean inverse monoids and dimension groups and stuff like that, which hasn't appeared yet because I haven't written it up. So there's more of that. There's also some stuff on characterizations where you just have a single finite symmetric inverse monoid, and then you take a direct limit of these things. What do you get? And MV-algebras play a role in that as well. So we, and this is different. This is different from the stuff that we did before, and is different from the stuff that Mundici did. And I think I better finish before we get thrown out. Thank you very much.
Going very deep, but I can still see you.
That's right, and we've used some of that stuff, yeah, in one of our in the later paper. So yeah.
I was just wondering, because your theorem somehow says something about every MV-algebra. So I wonder how does it look on the other side of the duality for multisets?
Yeah.
Is that something you?
Yeah, that was, we talked a lot about applying these results backwards. And the answer is I simply don't know. There's a huge amount of work on MV-algebras, and it should be applicable to Boolean inverse monoids somehow, but I don't know how.
Well, we're almost at the end of this session. Let's first of all,
thank you very much.
I just want to finish up. Robin, in his talk, he mentioned Phil's sense of humour and also the hat that he used to wear. And so I knew Phil and Marcia Scott, been friends with them for many years. And we first met when I moved to Montreal in 1983 to work there for a year. And Phil learned that I was going to, the next year I was going to move to Buffalo to work with Phil Lorvier. So he said, oh, you're moving to Buffalo. So he gave me a hat. I've got the hat here that Phil gave me. He said, well, when you go to Buffalo, everybody in Buffalo wears these hats. So make sure that when you get to Buffalo, you wear this hat. So I got there and I found it was